Welcome back to the show, everyone. Today we'll be taking a deep dive into a topic I'm sure you're somewhat familiar with, vectors.
Ah, yes, vectors. Those fascinating quantities that have both magnitude and direction.
Exactly. It's like they're a step up from those plain old scalars we always hear about.
Right, scalars. They only tell you how much of something you have, but with vectors you get the full picture.
You know the size and which way it's pointing. Like if you're driving a car, you might know your speed is 60 miles per hour.
That's a scalar, just a number. But if you add the direction you're heading north at 60 miles per hour, that becomes your velocity.
Ah, I see. So that's the difference between speed and velocity.
Precisely. Velocity is a vector because it incorporates both the magnitude, speed, and direction.
Okay, that makes a lot more sense.
Yeah.
Now we'll be using a physics learning module from Open Educational Resources, Open Source Physics at Singapore to explore this idea of vectors even further.
It's a great resource for diving into the concept of vector components.
Right, components. Now that's where things start to get really interesting.
It's like taking a vector and breaking it down into its fundamental pieces.
Okay, so imagine we have a vector pointing northwest.
You can think of it as having two parts, one part pointing north and another part pointing west.
Like it's moving both north and west at the same time.
Precisely. And those are its components. It's a bit like a right triangle, where the vector itself is the hypotenuse.
Ah, that's a helpful visual. So we're essentially splitting the vector into its horizontal and vertical parts.
Exactly. And this might seem like we're making things more complicated, but trust me, it actually makes calculations way easier.
I'm intrigued. How so?
Well, let's say you're trying to figure out how far a cannonball will travel horizontally after it's been launched.
I can see how dealing with that whole diagonal vector all at once would be pretty tricky.
Right. But if we break down the initial force vector into its horizontal and vertical components, things become much more manageable.
So we can kind of isolate the part of the force that's pushing the cannonball forward.
You got it. The
Yep.
horizontal component tells us exactly how much force is acting in that direction.
And I'm guessing the vertical component tells us how much force is acting upwards.
Precisely. It's all about separating the vector into its individual effects.
Okay. I'm starting to see the power of this component approach, but how do we actually go about calculating these components?
Well, the source material mentions a couple of handy formulas.
Formulas. Oh boy, I hope it's not too math heavy.
Don't worry.
Yeah.
We'll keep it light. But these formulas help us relate the vector's magnitude, angle, and components.
So let's say our cannonball is launched with a force of 50 newtons at an angle of 30 degrees above the horizontal.
Perfect. To find the horizontal component, which we'll call x degrees, we can use this formula. X equals a cos theta.
Okay, let me break that down. So A represents the magnitude of the vector, which is 50 newtons in this case.
That's right. And theta represents the angle, which is 30 degrees.
So we're taking the cosine of the angle and multiplying it by the magnitude.
Exactly. And the cosine of 30 degrees is about 0.87.
So ACUS would be 50 newtons times 0.87, which is roughly 43.5 newtons.
Precisely. That's the horizontal component of the force acting on the cannonball.
Wow, so we've isolated the exact force that's propelling it forward. And I'm guessing there's a similar formula for the vertical component.
You bet. It's I, S in theta.
So we'd use the sine of the angle instead of the cosine.
Exactly. And in this case, the sine of 30 degrees is 0.5.
So I would be 50 newtons times 0.5, which equals 25 newtons.
That's right. That's the vertical component of the force.
So by using these formulas, we can figure out the horizontal and vertical forces separately.
And that allows us to analyze the cannonball's motion in both directions independently.
This is making those formulas seem way less intimidating.
They're really just tools to help us understand the vector better.
It's like we're breaking down a complex problem into smaller, more manageable pieces.
Exactly. And this component approach isn't just limited to projectile motion either.
Oh, really? Where else could we apply this?
Think about forces acting on a bridge or currents in a river.
I can see how understanding the horizontal and vertical components of those forces would be crucial.
Absolutely. It's all about breaking down a vector into its fundamental parts to gain a deeper understanding of how it influences the world around us.
This is starting to feel like we're uncovering a secret code for understanding motion and forces.
That's a great way to put it.
It seems like this component approach could have applications far beyond just physics problems.
Absolutely. Think about it. We've been exploring vectors on a flat surface like a piece of paper. But what happens when we add another dimension and step into the world of 3D vectors?
Ooh, 3D vectors. This is where things start to get really interesting.
It is, and we'll delve into that fascinating realm in the next part of our deep dive, so stay tuned.
Okay, so we're stepping into the world of 3D vectors. Like we're in a spaceship now, exploring a whole new dimension.
Exactly. And it all starts by adding one more component to the mix.
So instead of just horizontal x and vertical y, now we have...
A z component. Imagine an axis going straight up and down. That's our z direction.
Ah, okay, so now our vector can point not just north, south, east, or west,
But also up and down. It's like going from a flat map.
to a 3D model of the world.
Exactly. Think of it like this. In 2D, we can describe a location on a map using coordinates, like 3, 4.
Right, representing how far east and north we are.
But in 3D, we add a third coordinate to specify height. So a point in space might have coordinates like 3, 4, 2.
Meaning 3 units east, 4 units north, and 2 units up.
Precisely. So a 3D vector would essentially tell us how far to move in each of those 3 directions.
Okay, I think I'm starting to wrap my head around this. So just like with 2D vectors, we can still break down a 3D vector into its components.
Exactly. And this becomes especially important when we're dealing with things like, well, you mentioned spaceships.
Right. I can imagine in aerospace engineering, understanding the precise direction and magnitude of forces acting on a spacecraft in 3D would be crucial.
Absolutely. You need to know how those forces are affecting the spacecraft's movement in all 3 dimensions.
It's like those vectors are the language of motion, whether we're talking about a cannonball or a spaceship.
They really are. It's a universal concept. Yeah. And speaking of universal concepts, there's another fascinating aspect of vectors that I think we should touch on.
Oh, what's that?
Vector fields.
Vector fields. Now those sound a bit intimidating.
They might sound complex, but think back to how we talked about breaking down individual vectors into their components.
Right, like splitting that northwest vector into its north and west parts.
Now imagine having a vector at every single point in space, each with its own magnitude and direction.
Whoa, okay, my brain is trying to picture that. It's like every point in the universe has a tiny arrow attached to it.
You got it. It's like a map showing how a vector quantity changes over an area or volume. That's what a vector field is.
Okay, can you give me a real-world example?
Sure. Take a magnetic field, for example. Every point around a magnet has a magnetic field vector associated with it.
Ah, like those diagrams we used to see in science class, with the lines showing the magnetic field around a bar magnet.
Exactly. Those lines are a simplified representation of the vector field. At every point on those lines, there's a vector showing the direction of the magnetic force.
So the lines are just a visual guide, but the real action is happening with all those invisible vectors.
You got it. And the closer those lines are together, the stronger the magnetic field at that point.
It's like a visual representation of an invisible force field.
Precisely. And understanding these vector fields is crucial in so many areas. Think about MRI machines or studying the Earth's magnetic field, which protects us from harmful solar radiation.
Okay, I'm starting to see the bigger picture here. It's not just about individual vectors. It's about how these vectors change and interact throughout space.
That's a great way to put it. And it's not just magnetic fields either. Vector fields can be used to describe all sorts of phenomena. Electric fields, gravitational fields, fluid flow.
Whoa, so vector fields are kind of like a universal language for describing how things change and interact in the world.
Exactly. It's a powerful concept that helps us understand the forces and patterns that shape our universe.
This is seriously blowing my mind. Vectors are way more intricate than I ever imagined.
They are. There's one more twist I want to throw in. Not everything with magnitude and direction is automatically a true vector.
Wait, really? I thought if it had a size and a direction, it was a vector? What else is there?
Well, true vectors have to follow certain rules, specifically the rules of vector addition.
Ah, okay. So it's not enough to just have magnitude and direction. You have to behave in a specific way when you're combined with other vectors.
Precisely. Think about the classic example of walking. If you walk 3 blocks east and then 4 blocks north.
You're not simply 7 blocks away from where you started.
Right. Your final displacement, which is a true vector, is 5 blocks in a northeast direction.
Because we're not just adding the distances, we're adding the directions too.
Exactly. And there are some quantities that might seem like vectors at first glance, but they don't quite follow these rules of addition.
Oh, interesting. Like, well, the source mentioned something about angular displacement and electric current.
Let's take angular displacement. Imagine you're spinning a wheel. We can describe its rotation using an angle and a direction, clockwise or counterclockwise.
So it seems like it should be a vector. It has both magnitude and direction.
You'd think so. But when you start combining rotations, they don't always behave like true vectors under addition.
I'm a bit lost. What do you mean by behave like true vectors?
The final result of combining those rotations can actually depend on the order in which you perform them.
Oh, so the order matters.
It does. And that's not something that happens with true vectors. They always follow those rules of addition regardless of the order.
That's a really cool nuance. So it's not enough to just have magnitude and direction. You have to play by the rules of vector addition, too.
Got it.
This deep dive is really making me appreciate all the complexity hidden within these seemingly simple concepts.
It's fascinating, isn't it? And speaking of complexity, have you ever wondered how those incredibly realistic visuals in video games and animated movies are created?
Actually, yes, I was just thinking about that. It's amazing how lifelike computer graphics have become.
Well, believe it or not, vectors play a huge role in that as well.
Really? I had no idea.
Oh yes, vectors are the backbone of computer graphics. Imagine you're designing a 3D model of a car in a video game.
Okay.
Every single point on that car's surface is defined by a vector in 3D space.
So the car is basically a collection of vectors.
Exactly. And when that car moves or rotates in the game, those vectors are manipulated mathematically to create that smooth, realistic motion on your screen.
That's incredible. So all those cool stunts and explosions we see in movies, it's all thanks to vectors working behind the scenes.
Precisely. And it's not just movement either. Vectors are also used to define things like lighting and shading, creating all those stunning visual effects that make the graphics look so real.
Wow, I never realized vectors were so deeply embedded in the technology we use every day.
It really highlights their versatility and power. They're a fundamental concept that bridges the gap between abstract math and the tangible world around us.
This has been such an eye-opening deep dive, from understanding how things move to visualizing invisible fields to creating realistic computer graphics. Vectors are everywhere.
They truly are. And we've only scratched the surface of this fascinating subject.
I'm definitely feeling inspired to learn more.
That's great to hear. There's always more to discover.
So we were talking about how vectors are like the hidden language of computer graphics.
Yeah. It's amazing how they're used to create those stunning visuals we see in games and movies.
And I think that actually ties in nicely with another fascinating aspect of vectors that we touched on earlier, vector fields.
Right. We talked about them a bit in the context of magnetic fields.
Yeah, like those diagrams with lines showing the magnetic field around a magnet.
But those lines are actually a simplified way of representing something much more complex. A vector field assigns a vector to every single point in space.
So instead of just one vector, we're talking about an infinite number of vectors.
Exactly, each with its own magnitude and direction. It's like, imagine a room filled with air. At each point in that room, there's a tiny arrow indicating the direction and speed of the airflow.
So it's like a visual representation of how the air is moving throughout the entire room.
Precisely. That's a vector field representing the wind patterns in the room.
Okay, I'm starting to get the picture. So a magnetic field is kind of like that, but instead of wind, we're talking about magnetic forces.
You got it. Every point around a magnet has a magnetic force vector associated with it.
So the lines we see in those diagrams are just connecting points where the vectors have the same direction.
That's right. It's a way to visualize the overall pattern of the field. But the real action is happening with all those invisible vectors at every point in space.
Wow. It's like there's this whole hidden world of vectors operating behind the scenes.
And by understanding these vector fields, we can predict how those forces will act on objects within the field.
Like how a compass needle will align itself with the Earth's magnetic field.
Exactly. And it goes way beyond just compasses. This is crucial for designing things like electric motors.
And even for studying things like how the Earth's magnetic field protects us from solar radiation.
It's amazing, isn't it? Those seemingly abstract mathematical tools have such profound real-world implications.
It's like we're uncovering the secrets of the universe one vector at a time.
And this is just the tip of the iceberg. Vector fields are used to model all sorts of phenomena.
Like electric fields and gravitational fields?
Exactly. Even fluid flow. It's a powerful concept that helps us understand the forces and patterns that shape our world.
Well, this deep dive has been a truly mind-blowing experience.
I'm glad you enjoyed it.
We started with the simple idea of a vector, a quantity with both magnitude and direction.
And we explored how breaking down vectors into components can help us analyze motion and forces.
We even ventured into the world of 3D vectors and those incredible vector fields.
It's been quite a journey.
I have to say, I had no idea just how important and versatile vectors were before we started this deep dive.
It's one of those foundational concepts that often goes unnoticed, but it truly underpins so much of our understanding of the physical world.
I'm definitely feeling inspired to learn more and explore this fascinating subject further.
That's fantastic to hear. Curiosity is the key to unlocking new knowledge.
Well, on that note, it's time to wrap up our deep dive into the world of vectors. A huge thank you to our expert for guiding us through this incredible journey.
It was my pleasure.
And to our listeners, we hope you enjoyed this exploration as much as we did. For those who want to delve even deeper, we've included links to some fantastic resources in the show notes, so be sure to check those out.
Let's keep those brains buzzing.
Until next time, stay curious.